Hello, I'm Val Browning, and today I'm going to be taking you through the AP Physics C Mechanics second free response question from 2005. And this question deals with Kepler's three laws of planetary motion, the ability to use equivalent formulas for gravity, understanding proportionality between variables and using them to solve graphing questions, plotting points on a graph and finding the slope, and knowledge of centripetal forces. This is just for this problem. These are not like the required skills for the AP exam in general. This is just for this free response question in particular. Okay, the first thing we want to talk about are Kepler's three laws of planetary motion. The first two we're not really going to deal with for this question, and you don't need to deal with them too much for the free response portion of the AP exam. It's just good to know them in general. But the third one is the one we're concerned about for this question, which states that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit, which is really just saying t squared is proportional to r cubed for any orbiting body. Alright, the second thing we want to review are the formulas for gravity to be used in this problem and centripetal forces in general. Now, based on these two pictures, you can clearly see that if you have an orbiting body, such as the moon around the Earth, there's an equal and opposite vector direction gravitational force between the moon and the Earth. So the moon pulls on the Earth with a gravitational force, and the Earth pulls on the moon with a gravitational force. And this is what causes the tides on the Earth, is the moon's gravitational force pulling on it. And in this second picture, you can see a more like physics-style diagram of a body of mass m orbiting around this blue dot, which could be a sun or a star, and this m could be the Earth. And for example, the velocity vector is going to always point tangential to the orbital path. The radius that we're talking about here, and the radius of Kepler's third law, is the radius on average between the Earth, or the body orbiting, and the body being orbited. It's that distance. And the force of gravity is also the same as the force centripetal, and centripetal force just means along the radius towards the center of the orbit. And here we have the formulas that we're going to need for this question. Force of gravity is equal to mass times the local gravity, which we use all the time on Earth, using little g as 9.8 meters per second squared. And the second equation comes from the equation sheet, which you get on the AP exam, and this is the force of gravity between two objects, any two objects, is equal to the gravitational constant big G times the mass of the first object times the mass of the second object, and that quantity over the radius, or the distance between the two objects, squared. And down here, we just have this simple equation for centripetal force, net centripetal force, which equals m times the velocity squared. So m is the mass of the object that is doing the orbiting. So in this case, it'd be the m, or in this case, it would be the moon, over the radius between the two objects, or the radius between the object orbiting and the center of its orbital path. Alright, here's a quick review of proportionality to be used for this graphing question. If we have a straight line, and you learned this in Algebra 2 and geometry, you know that y equals mx plus b, where y is the dependent variable, x is the dependent variable, m is the slope, and b is the y-intercept, or the initial value in physics. And this is going to come in handy. I've done this little color coding where you can see all these pieces of this equation. And just to give you a physics example, I took an equation from the equation sheet. This is the kinematic equation for final velocity. And you can see that final velocity is the independent variable, because if you look on this graph, this velocity time graph down here that I've made, it's on the y-axis, is equal to the acceleration times time which acceleration is going to be the slope, and you can see that on this graph, and you know that from your stacks of graphs, times the time, which is the independent variable on the x-axis, plus the initial velocity. And here in this velocity time graph, we've got initial velocity as being 0 meters per second. So this equation mirrors this y equals mx plus b equation, and you can clearly see that I've already said this y equals mx plus b equation earlier. And here's another picture. Hold on, I'm just going to get this to stop appearing on my screen. Okay. Whoa. Alright. So this m is going to be the slope, b is going to be the y-intercept, and you have x and y as your axes. And that's going to come in handy later. Alright, here's the problem that we're presented with. A student is given the set of orbital data for some of the moons of Saturn shown below and is asked to use the data to determine the mass m of Saturn. Assume the orbits are circular. Alright, so that tells us we don't need to worry about Kepler's law of elliptical orbits. Alright, so you can read the parts for yourself if you pause the video right now. I'm not going to go through and read each one, but we will get to each of these problems in just a second. Alright, part A. Part A asks us to write an algebraic expression for the gravitational force between Saturn and one of its moons. Based on what I told you earlier about the formulas for gravity we need for this specific free response question, you know from the equation sheet that the force of gravity between any two objects is g m1 m2 over r squared. And we're going to do some basic variable substitution here, and we're going to say m1 is going to be the mass of the moon, and m2 is the mass of Saturn. It really doesn't matter which one, if you call m1 the mass of Saturn or the mass of the moon, just that you have two separate masses being multiplied in this equation. So, once we substitute in our m1 and m2, we get force of gravity between the two objects is big G, or gravitational constant, times the mass of the small moon times the mass of Saturn, and that quantity over the radius, which is the distance between them, squared. And that's all you have to do for part A, really. Part A is really setting you up for part B, which asks us, and this is kind of the meat of the question, it says use your expression for part A and the assumption of circular orbits to derive an equation for the orbital period t of a moon as a function of its orbital radius r. Alright, the way to start off this question would be to say that you have your force of gravity, and for this question I'm going to leave the masses as m1 and m2 because I don't want to write out m moon and m sat every single time. So I'll just fill you in as to which of those I'm calling m1 and m2. So if you look at these two pictures, you can see that the force of gravity between the two objects is also equal to the net centripetal force of the object. So basically, the force that the Earth pulls on the moon with is also equal to the net centripetal force acting on the moon, because gravity is the only two forces acting between these objects. So here I've written the formula for gravity between two objects, and here I've written the formula for net centripetal force acting on an object, and in this case the object will be the moon orbiting around Saturn. Okay, so we can make the statement that the net centripetal force acting on the moon is equal to the force of gravity between the two objects. Now what we're going to do here is we're going to say the net centripetal force acting on the moon, which is the moon is going to be m1 in this problem. So here we've taken basically the net centripetal force equation, and we've set it equal to the gravitational force between two objects equation. Okay, so doing a little bit of algebra, these r's are going to cancel with each other on both sides, and the m1s, which is the mass of the moon, are going to cancel with each other on both sides, which leaves us, after solving this equation for v squared, because that's what we're going to need for the period, we get v squared equals g times m2 over r. And remember that, or I guess it'll be on the page, but that'll be important in a minute. Now, what we have to think about in this problem to get the period involved in this is that velocity of the moon is equal to distance over time. Velocity for any object moving is distance over time. So in this case, the distance that the moon is going to travel in a certain period of time will be 2 pi r, because that is the circumference of the circular orbit that the problem tells us to assume. So once you make the assumption of circular orbits, you can say that the distance traveled by the moon in one rotation or one complete trip around Saturn is going to be 2 pi r over the period, the orbital period of the moon, which is what we're trying to find in this, or we're trying to come up with an expression for that in this problem. Okay. So basically the next part we need to do is we take our velocity we found from d over t and we square that, so that we'll get a v squared, which is what we had earlier in our other solution for our other equation. And we get v squared equals 4 pi squared r squared over t squared. Simple stuff. That comes from the 2 pi r over t. And we're going to plug this v squared in right here for the v squared that we got out of our force of gravity and net centripetal force equation. And we're going to set 4 pi squared r squared over t squared equal to g m2, which m2 is the mass of Saturn, over r. Okay, now solving this equation for t squared gives us 4 pi squared r squared quantity over g m2 over r equals t squared. Now on the AP exam, they accept either one of these. You can either leave this equation in terms of t squared, or you can square root both sides and say t equals square root of all this on this side, and either answer is valid. The reason I leave it as t squared is just because I don't want to deal with the square root later on in the problem when we have to do graphing. Alright, part C says which quantities should be graphed to yield a straight line whose slope could be used to determine Saturn's mass. Now, going back to our proportionality review, we know that the equation for a straight line is y equals mx plus b. And we know that the equation we came up with for the period of the moon is equal to, or t squared is equal to 4 pi squared over gm2 times r cubed. And the reason I added the plus 0 onto there is just to show you how this equation mirrors the y equals mx plus b. In this case, the two variables that we have, the reason we're not calling m2 a variable in this case is because we know it's a constant. We know it's not going to change, and that's what we're trying to find with the slope. So we want to leave m2 in the slope so that we'll be able to use it later to once we complete our graph. So t squared is our dependent variable, and r cubed is our independent variable. And the plus 0 I just put there because there's no intercept here, so we're just going to leave it as 0. But if there were an intercept, that's where it would go in the equation. So the quantities that should be graphed are t squared and r cubed. Okay, part D asks us to complete this data table, which they give to you exactly like this on the problem, by calculating the two quantities to be graphed. Okay, the quantities we said should be graphed are t squared and r cubed. Now, there is another way to do this, which is a little bit more complicated, but if you took your original equation relating t squared and r cubed, and you square rooted both sides so that you had, here, let me go back, you had t equals square root of 4 pi squared r cubed over gm2, then you could, in theory, leave this as t, leave this column as t, and graph and plot in this column r to the 3/2, because you would have an r cubed underneath the square root. And that's okay, and that's completely valid, but the reason I kept it as t squared versus r cubed was for this exact reason. I didn't want to waste time by going through the calculator and doing all of these r calculations to the 3/2 power, because I felt like I could mess that up pretty easily. So I decided to do it in the t squared versus r cubed manner, because that's what I'm more familiar with. Okay, so the way you fill out this chart is basically you get your graphing calculator, and you don't need a graphing calculator for this, but it makes it easier. And you go into your lists from your stat button, so stat and then edit, and you fill out one of your lists with the information given to you about the period, and you fill out another list with the information given to you about the radius. And then in your next two lists, you make one list as the period squared, and so if your first list was L1, for this first list you have to fill in, you just say L1 squared for the whole entire list, and it would automatically fill it out. And you do the same thing with L2 cubed, so this list cubed would go here, and these are the values you would get if you did it the t squared versus r cubed way. And even just looking at this, you can see that the values, ignoring the E10 and E25, those just mean times 10 to the 10th and times 10 to the 25th. That's really what that means. You can see that 0.663 is pretty close to 0.63. You can see that 1.4 is pretty close to 1.3, and 2.7 close to 2.6, and 5.6 close to 5.4. So you know your slope is going to be pretty linear because these values are increasing like similarly to each other. Okay, so you would just write, and make sure you don't forget to write your units squared and your units cubed up here, or else you'll lose a point off of this part. Alright, part E. Part E is the second meat of the question. It's like the second patty if it were like a Big Mac or something. And it asks us to plot the graph on the axes below, and they give you this big graph. Label the axes with variables used and appropriate numbers to indicate the scale. Now, going back to the equation that we found relating t squared and r cubed, we know that t squared has to be the dependent variable because it's the y in this problem, so it will go on the y-axis, and r cubed is the dependent or the independent variable, so it will go on the x-axis. All right. So I've put radius cubed, and for simplicity's sake, I put meter cubed times 10 to the 25th in the units, so I don't have to write times 10 to the 25th after each of my values. And I label my axis from 0 to 6 because that's the scaling, the correct scaling that we need, because if we go back, we know that the radius cubed goes from about 0 to 6, and so does the period. So we're going to just use 0 to 6 for our scaling on each of these. And on the y-axis, I've put period squared, and I've put second squared times 10 to the 10 power, and I've labeled it 0 to 6. Alright, so now the rest of this question is simple data input. So here's one of the points, and I'm just going to label the points. Nothing really to talk about here, like, you know, you just label your radius, and you're labeling these from the part of the table that you had to input, not the table that the problem already gave you. And you can notice already that this is a linearized graph. So we draw a line of best fit, and you're going to get ranging, you're going to get variable slopes, but as long as you're pretty close, you're going to get the points for this problem. And this is how I did it on my paper, but for the first point of which we're going to analyze slope, I picked 2, 2. And for the second slope point, I picked 5, 5.2. And I put plus signs on here to indicate that these were the 2 points I was going to be using to take the slope, or to calculate the slope. For the next part, part F. Alright, part F asks us to use our graph and calculate a value for the mass of Saturn. Now you might see this problem and think, holy, how am I going to calculate a value for the mass of Saturn just by using the slope? Now, the common way to think about this problem, which some students might think of, is, oh, the slope just equals the mass because reasons. And that is going to be wrong. You can't think about this problem this way for this reason, and I'm going to go back a couple of slides. Alright, back to this equation. I've put everything in blue that is the slope. So all this blue stuff, 4 pi squared over gm2, that is the slope of this graph. Now, if you're asked to find the mass is m2 of Saturn. the mass is not equal to this entire quantity right here. Now, the slope is equal to this entire quantity, but not the mass. So that's why you can't say that the mass is equal to the slope. Alright, let me get back to where I was. Okay, so I've taken the points that I want to use to find the slope, and I've stated that the slope is equal to m, and don't confuse that with mass, this is just slope, equals delta y over delta x, or change in y over change in x. The next thing I did was I calculated a value for the slope, and I did this by just simple slope calculations between 2 points. You should know how to do this already. And I got 1.07 times 10 to the negative 15th second squared per meters cubed for the slope. And this is a ridiculously small number, so your intuition should go ahead and tell you that there's no way this is the mass of an entire planet. Alright, now the next thing we have to do is, and this kind of cut off, I don't know why, but just pretend this r cubed is up here. So we have t squared equals 4 pi cubed over gm2 times r cubed, and this is the equation we've been looking at the entire time, and we know that everything in blue here is going to be the slope of this equation, or of the graph that we plotted. And I've stated that here by making a point and then putting m for slope. Alright, if we know that entire quantity is the slope, we can go ahead and say that the slope we found from the graph is equal to the slope from the equation. And doing a little bit of algebra, we can see that 4 pi squared over big G times the slope we found from the graph, using the 2 points, is equal to m2, also the mass of Saturn. And putting this into our calculator gives us a mass of 5.532 times 10 to the 26th kilograms for the mass of Saturn. And that looks to be pretty correct. I mean, it's pretty big, and you could go ahead and assume that that's around about the mass of Saturn. I looked it up, and the mass of Saturn is about 5.6 times 10 to the 26th kilograms, so we're on the right track, and the AP exam would definitely have this answer in its range of possible correct answers. Thank you for watching, and I hope you learned something from this. I spent a while putting this PowerPoint together for y'all, and if you have any questions, just ask Mr. Gussman. He's a great teacher. Alright, thank you, and goodbye.